Off the coast of Scotland, you could witness this. Wind turbines being put into the water. They're called tidal turbines. They sit on the seafloor and harness the energy in the moving water that comes in and goes out with the tides.
Tidal power just kind of sitting there and waiting to be used.
The potential is huge. It's estimated that we could practically capture enough tidal energy to power all homes in the United States twice over.
And my research with climate change shows we need this energy now.
Yet, at the moment, all the energy we get from existing tidal power plants worldwide can power less than 400,000 homes. So how does tidal power work exactly? And why isn't it everywhere yet? With tidal power, there's one word that comes up a lot.
Predictable.
Predictable.
Predictability.
Tides are predictable. They come in, they go out, and they've been doing this the same way since the moon was born. But before we jump into how it all works, let's do a quick high school science refresher on the tides. The moon's gravity pulls at the Earth, and water, which can move more freely than solid ground, begins to bulge towards it. On the other side, a differential force by the Earth's own gravity causes an opposing bulge too. When the Earth aligns with the moon and the sun's gravity makes the bulge even more intense. So the Earth rotates through the bulge, and wherever you are in the world, you are either entering the bulge or leaving it behind, which looks to us like the tide is coming in or going out. This cycle happens around twice a day. In case you're wondering what happens when the moon is in a different phase, the bulge just gets weaker. Tidal power takes advantage of these tides. Other ocean technologies also look at waves and ocean currents, but that's a whole other story for later. So with the tides, stick a turbine in the water as it flows in or out, and voila, you can make electricity, with the same principle that wind turbines use. Moving water makes the turbine spin. This powers a gearbox and a generator, which turns mechanical energy into electricity. Water, incidentally, is over 800 times denser than air, which means that tidal turbines need to be sturdier, but they can be smaller and slower and still individually produce more power than wind turbines. So far, so good? Then back to tidal's trump card, predictability. Wind starts and stops blowing somewhat randomly, and the sun isn't always out. So these renewables can be difficult to integrate into the grid. Tides, as we know, are really predictable and consistent. So if batteries are charged when tides are flowing, we could use those batteries each time there's no movement and repeat at regular intervals. The other option is fossil fuels, but let's not even go there. The younger and sexier kind of the market, tidal stream power. It's showing more promise at the moment with its simpler devices that depend on underwater currents caused by the tides. They vary in shape and design. The most common are breeze turbines, like wind turbines, that can be set up in clusters in wind farms underwater. A couple of research and development zones in the north of Scotland supplied record-breaking levels of clean energy to the UK grid this year, powering over 12,000 homes for a year. Then there's an underwater kite that flies in a figure of 8. Like the wind lifts a kite, currents in the water speed it up, in turn producing more energy. And then there are floating steam turbines, the most powerful of which was recently launched in Scotland with an individual turbine capacity of 2 megawatts. They're tethered to the seafloor, but the turbines remain close to the surface, which means the undersea work is cheaper and they can be moved around. Compared to wind or solar energy though, tidal has been slow for a reason you might have guessed.
Sadly, a lot of the solutions are really expensive.
Amanda Smythe is the go-to tidal researcher at Oxford University who believes tidal's time will come.
Because the industry is so young, so it's a very small industry, it doesn't have an established supply chain or manufacturing chain. Anytime you're going to operate something underwater, that has its own unique set of engineering challenges. Your standard ones like corrosion is going to be a big problem, so you're going to have to choose your materials really carefully. Biofouling is a really big issue. where, you put something in the water, things are going to want to grow on it, and it's going to make it into a little mini reef, a little habitat. The performance of the turbine will deteriorate, so you need to find some way of preventing that. That's a huge operational cost.
Which is why most tidal stream generation projects cluster in the global north, where financial support to test the technology at this stage exists. China and South Korea are joining in, but lower-income countries like India have been slow or dropped plans to try out tidal power. But they could benefit when the costs of deployment begin to fall.
The challenge now is to bring down the price tag of it, to make sure that it is something that's commercially viable. And this is where things like sort of investments and government support and subsidies can be extremely impactful. There's a number of proven concepts, and there's a number of companies that have a technology ready.
While the UK and Canadian governments have been the biggest investors in tidal power, overall, grants and government investment have been slow, with less than 0.02% of annual investment in renewables reaching tidal. And so it's been behind the curve in other ways too. Electricity from underwater tidal turbines can cost up to 9 times that produced by turbines above the surface of the water. But the industry targets that life cycle costs could fall to 10 cents per kilowatt hour by the end of the decade, which would be pretty cheap. But apart from cost, what actually happens when you put these turbines underwater? Oceans are abundant with marine life. The structure of the Laurence project from earlier decimated the populations of 2 fish species. And like wind turbines that have been known to cause the lungs of bats flying past to implode, the pressure difference caused by tidal barrages could have a similar effect on the internal organs of fish. But tidal stream projects are already more eco-friendly.
Tidal turbines turn quite slowly. So the idea of things getting chopped is going to be, probably not going to happen. Things getting hit, yes, that can happen, especially at tip speeds. The big problem is not probably going to be collision. The problem is going to be displacement, that animals will avoid these areas and therefore not use these areas to feed in. And these faster tidal areas are areas that seabirds, mammals, and fish species do feed in.
Beth Scott studies the impact of tidal power on marine life around the world.
We've compared it to climate change. And even by 2050, what you see is climate change is 10 times worse than taking the maximum amount out of tides. And when we model that against animals and animal distributions, what we see is climate change is by far the worst enemy. So yes, these things will have environmental effects, but we should put them in that context of climate change.
Tidal has other benefits too. While its financial cost is still higher than other renewables, its net benefit could actually be higher when you consider things like its predictable supply of clean energy to the grid, or the fact that stream projects don't visually affect a beautiful sea view. So especially in coastal or island nations, tidal does have the power to play a significant role in getting to net zero in a relatively less disruptive way. The need of the hour is to make tidal power competitive.